Look up at the stars tonight, and you might think you're seeing the universe as it truly is, but what if everything out there is playing tricks on us? The cosmos is far stranger than we ever imagined, filled with phenomena so bizarre they challenge the very foundations of reality. From particles that communicate instantaneously across vast distances to invisible forces shaping the fate of galaxies, the universe is hiding secrets that defy logic and stretch our understanding to its limits. Today, we're embarking on a journey through 18 of the most astonishing clues that reveal just how little we truly know. These aren't just scientific curiosities, they're cosmic riddles that force us to question whether reality is even what it seems. Think about the last time you felt certain about something, like the solid ground beneath your feet or the predictable rise of the sun each morning. Now imagine discovering that certainty itself might be an illusion. The universe operates by rules so peculiar that even the brightest minds struggle to make sense of them. Take quantum entanglement, where two particles can mirror each other's actions instantly, no matter how far apart they are. Or dark matter, an invisible substance that outweighs everything we can see, yet refuses to reveal itself except through its gravitational pull. These aren't just abstract ideas. They're clues pointing to a reality far more mysterious than our everyday experience suggests. What if the universe is less like a clockwork machine and more like a puzzle with missing pieces? Every discovery we make seems to lead to deeper questions, pulling us further into the unknown. This video isn't just about listing strange phenomena, it's about exploring how these clues force us to rethink everything. Are we living in a hologram? Is time an illusion? Could there be hidden dimensions just beyond our perception? By the time we're done, you'll see the night sky, and maybe even your own existence, in a whole new light. So let's dive in, because the cosmos has been waiting to reveal its secrets, and what we uncover might just change the way you see reality forever. The first clue that shatters our ordinary understanding of the cosmos is something we can't even see: dark matter. Picture this: every galaxy spins so fast that it should tear itself apart, yet something invisible holds it together with an unshakable grip. That something is dark matter, a ghostly substance that makes up 85% of all matter in the universe. It doesn't emit light, reflect it, or interact with ordinary matter in any way except through gravity. We know it's there because without its hidden pull, galaxies would fly apart, and the universe as we know it wouldn't exist. Think of it like standing in a room where you can't see the walls, but every time you throw a ball, it bounces off something unseen. That's how scientists detect dark matter, by watching how its gravity bends light from distant stars or how it tugs on galaxies like an invisible puppeteer. The strangest part, after decades of searching, we still don't know what it's made of. It could be particles we've never detected, or something even more exotic, like remnants from the birth of the cosmos. Some theories suggest dark matter might be woven through hidden dimensions, or that it's evidence of parallel universes brushing against our own. And here's where it gets even weirder: dark matter isn't just holding galaxies together. It's also sculpting the large-scale structure of the universe, acting as an invisible scaffold guiding where galaxies form. Without it, the cosmos would look completely different, and life as we know it might never have had a chance to emerge. Yet despite its overwhelming presence, dark matter remains one of the biggest unsolved puzzles in physics. Every experiment designed to catch it has come up empty, leaving us with more questions than answers. Could it be that we're missing something fundamental about the nature of reality itself? One thing's for certain: until we solve the mystery of dark matter, we're only seeing a fraction of the true universe. If dark matter is the universe's invisible scaffolding, then dark energy is its mysterious engine pushing the cosmos apart faster and faster in defiance of gravity itself. Here's the astonishing truth. In the late 1990s, astronomers made a discovery that shattered expectations. They found that instead of slowing down over time, the expansion of the universe is accelerating. Something was overpowering gravity on the grandest scale imaginable, and they called it dark energy. Think of it like blowing up a balloon with tiny dots on its surface. If the balloon expands at a steady rate, the dots move apart predictably. But what if the balloon suddenly started inflating faster and faster, as if an unseen hand were pumping air into it at an ever-increasing speed? That's what dark energy is doing to our universe. The most puzzling part, we have no idea what's causing it. Some theories suggest dark energy is an inherent property of empty space itself, a constant energy field woven into the fabric of reality, growing stronger as the universe expands. Others propose it could be evidence of an undiscovered fifth fundamental force, or even a sign that our understanding of gravity is fundamentally flawed. The implications are staggering. If dark energy continues unchecked, it could lead to a future where galaxies beyond our local group accelerate away so fast that their light can never reach us again. The universe would become a vast, lonely expanse, with civilizations of the far future unable to see any stars beyond their own galaxy. It's a sobering thought, one that makes dark energy not just a scientific curiosity, but a force that could dictate the ultimate fate of everything. Yet despite its colossal influence, dark energy remains almost entirely enigmatic. Unlike dark matter, which we can indirectly detect through its gravitational effects, dark energy reveals itself only through the universe's accelerating expansion. Current experiments, like mapping the large-scale structure of the cosmos or studying the cosmic microwave background, are piecing together clues. But for now, dark energy stands as one of the greatest mysteries in physics, a reminder that the universe still holds secrets capable of rewriting everything we think we know. Just when you thought the universe couldn't get any stranger, quantum entanglement comes along and turns everything we know about reality upside down. Imagine two particles born from the same event, separated by millions of light years, yet when you change the state of one, the other instantly responds, as if distance means nothing at all. Einstein called this spooky action at a distance, and even he couldn't wrap his head around it, dismissing it as impossible. But here's the wild part. Experiment after experiment has proven it's real. Picture tossing a pair of gloves into opposite ends of the universe. If you find one glove is left-handed, you instantly know the other is right-handed, no matter how far apart they are. That's the basic idea behind entanglement, but with quantum particles, it's not just about hidden properties. The act of measuring one particle forces its partner into a corresponding state, faster than light could ever travel between them. It's as if the universe has a hidden communication channel, bypassing the cosmic speed limit we thought was absolute. So what's really going on? Some scientists believe entanglement hints at a deeper layer of reality, where everything is fundamentally connected in ways we can't yet perceive. It's like the universe is a vast, invisible tapestry, with every thread subtly influencing the others. Others propose even wilder ideas, like multiple dimensions folding into our own, or the possibility that space and time aren't the bedrock of reality, but emergent phenomena from something far more mysterious. The implications are mind-bending. If particles can influence each other instantaneously across vast distances, could the universe itself be one giant quantum system? Could entanglement explain why the cosmos seems so finely tuned for life? Or is it a clue that our understanding of causality, the idea that cause must always precede effect, is incomplete? One thing's certain: quantum entanglement doesn't just challenge our theories. It forces us to confront the possibility that reality is far more interconnected and far stranger than we ever dared imagine. Now consider this: our galaxy alone contains hundreds of billions of stars, with planets orbiting them in numbers so vast it dwarfs every grain of sand on Earth. Statistically, life should be everywhere, yet when we listen, the universe echoes with silence. This is the Fermi Paradox, a cosmic riddle that asks one haunting question: where is everybody? Named after physicist Enrico Fermi, who famously posed it during a lunchtime conversation in 1950. This paradox highlights the staggering contradiction between the high probability of extraterrestrial civilizations and the complete lack of evidence for their existence. Think of it like standing in the middle of a bustling city at midnight, surrounded by skyscrapers with their lights on, but not a single person in sight. The eerie emptiness defies logic, with planets in the habitable zone of their stars discovered by the thousands, and the building blocks of life found throughout the cosmos. The odds seem overwhelmingly in favor of life arising elsewhere. Yet after decades of radio telescopes scanning the skies and probes scouring our solar system, we've found nothing. No signals, no artifacts, not even a single microbe beyond Earth. So what's really going on? Scientists have proposed dozens of theories, each more unsettling than the last. Perhaps advanced civilizations inevitably destroy themselves before they can spread across the stars, falling victim to war, environmental collapse, or runaway technology. Or maybe we're living in a cosmic zoo, with other species deliberately avoiding contact to let humanity develop undisturbed. Some suggest that interstellar travel is simply too difficult, trapping civilizations around their home stars like fish in separate ponds. Others entertain the chilling possibility that we're among the first, that the universe only recently became habitable, and life like ours is still exceptionally rare. Then there's the darkest explanation of all. What if we're truly alone? What if Earth is a statistical fluke, a 1 in a trillion accident in an otherwise lifeless void? The implications would be profound. It would mean every star, every galaxy, every breathtaking nebula exists without witness, and that we bear the sole responsibility of giving the universe meaning. But here's the twist: the Fermi Paradox might not be a paradox at all. Our search has barely begun. We've scanned only a fraction of the radio spectrum, and our ability to detect subtle signs of technology is still in its infancy. Alien civilizations might communicate in ways we can't yet perceive, using neutrinos, gravitational waves, or something beyond our current understanding. Or perhaps they're already here, hidden in plain sight, their presence indistinguishable from natural phenomena. One thing is certain: the silence isn't just a scientific puzzle. It's a mirror forcing us to confront our assumptions about life, intelligence, and our own future among the stars. Whether the answer brings comfort or existential dread, solving the Fermi Paradox wouldn't just tell us about aliens, it would reveal something fundamental about what it means to be human in a universe that may be far stranger and far lonelier than we ever imagined. What if everything around you, the stars, the trees, even your own thoughts, weren't real? Not in the philosophical sense, but literally. What if our universe were nothing more than an ultra-advanced simulation, running on some unfathomable computer built by a civilization far beyond our own? This isn't science fiction anymore. The simulation hypothesis has gained serious traction among scientists and tech visionaries, with figures like Elon Musk famously stating the odds we're living in base reality are 1 in billions. And when you start examining the evidence, it's hard to dismiss the idea outright. Take quantum mechanics, for example. At the smallest scales, particles behave like pixels in a video game, existing in fuzzy, undefined states until observed, as if the universe is conserving processing power by only rendering things when needed. Then there's the unsettling mathematical precision of the cosmos. Why do the laws of physics follow such elegant equations? Could it be because those equations are the underlying code of our reality? Even glitches in the system, like déjà vu or unexplained cosmic anomalies, have some wondering if we're catching fleeting glimpses of the program running behind the scenes. But here's where it gets even stranger. If we are living in a simulation, the creators could have embedded clues intentionally, like Easter eggs in a video game. Some researchers suggest that advanced civilizations might simulate their ancestors to study history, or that our universe is just one of countless simulations running in some higher dimensional server. The implications are dizzying. If true, free will might be an illusion, death could just mean the program ends, and the meaning of life reduces to something as mundane as data storage. Yet not everyone's convinced. Critics argue that simulating every particle in a universe would require impossible amounts of energy, unless the simulation is only rendering what we observe, like a cosmic version of the Matrix. Others point out that even if the math feels too perfect, that doesn't prove it's artificial. Maybe math is simply the language of reality. And then there's the existential kicker. If simulations are possible, and civilizations eventually create them, wouldn't the number of simulated realities vastly outnumber the real one? Statistically, we're probably in one, so how could we ever know for sure? Some scientists propose looking for pixelation in the fabric of spacetime, tiny, fundamental limits to how small or precise reality can get. Others suggest hunting for errors in physical constants, like the speed of light fluctuating in ways that betray underlying code. Until then, the simulation hypothesis remains the ultimate cosmic head-scratcher, a theory that's impossible to prove, impossible to disprove, and impossible to ignore. Whether it's true or not, one thing's certain: it forces us to confront how little we truly understand about the nature of existence itself. Black holes aren't just cosmic vacuum cleaners. They're the universe's ultimate shredders, crushing matter into oblivion. But here's the problem. According to quantum mechanics, information, the fundamental blueprint of everything that falls in, can never truly disappear. This clash between quantum rules and the brutal reality of black holes creates one of the most heated debates in physics, the black hole information paradox. On one side, Einstein's theory of relativity says black holes trap everything behind an event horizon, leaving no trace. On the other, quantum theory insists information must persist, even if it's scrambled beyond recognition. Picture tossing a book into a fire. The pages burn, but in theory, every word could be reconstructed from the smoke and ash if you had perfect knowledge of the particles. Now imagine tossing that book into a black hole. Relativity says it's gone forever, erased from existence, but quantum mechanics insists the information isn't lost, just hidden in ways we don't yet understand. The stakes couldn't be higher. If black holes really destroy information, it would mean rewriting the foundational laws of physics. So where does the information go? Some physicists, like Stephen Hawking, once thought it might leak back out as random thermal radiation, a cosmic game of telephone where the original message is garbled beyond recovery. Others propose wilder solutions, like the idea that black holes don't obliterate information but encode it on their surfaces like a hologram. This holographic principle suggests everything inside a black hole could be projected onto its event horizon, preserved in a two-dimensional quantum code. Then there's the most mind-bending possibility of all. black holes might not be endpoints but doorways. If information slips into another universe or dimension, it wouldn't be destroyed, just relocated where we can't access it. String theorists argue that black holes could be tangled knots of spacetime leading to entirely new realms, with the information emerging somewhere else, intact but irretrievable. Yet after decades of debate, the paradox remains unsolved. Experiments are nearly impossible. How do you test a black hole's secrets when even light can't escape? Some hope advanced math or breakthroughs in quantum gravity will crack the puzzle. Others wonder if the contradiction itself is a clue that our theories are missing something profound. Either way, the black hole information paradox isn't just about astrophysics. It's a battle for the soul of reality, forcing us to ask, does the universe play by rules we can ever fully understand, or are some truths forever beyond our grasp? Deep in the cosmic void, something massive is pulling us toward it, not with a tug, but with an inescapable gravitational grip. Meet the Great Attractor, a mysterious region of space so powerful it's dragging entire galaxies, including our Milky Way, toward it at over 600 kilometers per second. Hidden behind thick clouds of dust and stars in the constellation Centaurus, this enigma has puzzled astronomers since its discovery in the 1970s, when they noticed thousands of galaxies all streaming in the same direction, as if drawn by an unseen hand. What makes the Great Attractor so baffling isn't just its power, it's how little we can see of it. Imagine trying to identify a mountain range through dense fog, catching only glimpses of its silhouette. That's the challenge scientists face. Our view is blocked by the Milky Way's own galactic plane, a dusty band of stars and gas that obscures nearly 20% of the night sky. Even X-ray telescopes struggle to pierce through, leaving us with more questions than answers. At the heart of the mystery lies this question: what could possibly exert such force? Initial estimates suggested the Great Attractor might be a supercluster of galaxies, a colossal gathering of matter with a combined mass of tens of thousands of Milky Ways. But here's the twist: when astronomers mapped the motion of galaxies on an even grander scale, they realized the Great Attractor itself is being pulled toward something far larger. This led to the discovery of the Shapley supercluster, a staggering assembly of galaxies over 600 million light-years away, with gravity so immense it's yanking entire galaxy clusters into its orbit. Yet the plot thickens. Even Shapley might not be the end of the cosmic tug-of-war. Some researchers propose that the Great Attractor is just one piece of a vast, interconnected web of dark matter, filaments, invisible rivers of mass threading through the universe, guiding galaxies along invisible highways. Others speculate it could be a rare cosmic collision where multiple superclusters are merging, creating a gravitational hotspot that warps the motion of everything around it. The implications are profound. If the Great Attractor is part of a larger structure we're only beginning to map, it means our local universe is far more dynamic and far more mysterious than we ever imagined. Galaxies aren't just drifting randomly, they're caught in a cosmic current, swept along by forces we're still struggling to measure. So how will we ever solve this puzzle? New telescopes like the upcoming Square Kilometre Array aim to peer through the galactic dust with unprecedented clarity, mapping the hidden mass-distorting spacetime around us. Meanwhile, studies of dark matter's distribution could reveal whether the Great Attractor is a fleeting anomaly or a signpost pointing to even greater structures lurking in the shadows. One thing's certain: the Great Attractor isn't just a curiosity. It's a reminder that even as we unravel the universe's secrets, the cosmos keeps pulling us deeper into the unknown, literally. And with every galaxy it drags toward its heart, it challenges us to rethink our place in a universe where even the emptiest spaces are alive with invisible motion. On a quiet August night in 1977, a radio telescope in Ohio picked up something extraordinary, a burst of radiation so intense, so unlike anything natural, that the astronomer who discovered it scrawled, "Wow." In red ink on the printout, that single word would immortalize one of the most tantalizing mysteries in the search for extraterrestrial intelligence. The WOW signal lasted just 72 seconds, blazing across the frequency bands with a strength 30 times louder than the cosmic background noise. It matched the exact signature scientists predicted an alien transmission would have: narrowband, focused, and seemingly artificial. And then, just as suddenly as it appeared, it vanished, never to be heard again. What makes this signal so baffling isn't just its strength or its uncanny resemblance to an intentional broadcast. It's the fact that despite 40 years of repeated searches, listening to the same patch of sky in the constellation Sagittarius with ever more sensitive equipment, the silence has been absolute. No repeats, no echoes, not even a hint of a similar signal anywhere else in the cosmos. It's as if the universe played a prank on us, flashing a cosmic Morse code just once, then leaving us to wonder if we imagined the whole thing. So what could it have been? Skeptics point to more mundane explanations, like a passing comet reflecting radio waves or a secret military satellite test. But here's the catch: comets don't emit narrowband signals at the WOW signal's frequency, and no known human-made object matches its profile. The signal's frequency also lands in a protected, quiet zone, a range of radio spectrum where earthly transmissions are banned to avoid interference with deep space listening. That means if it was human-made, it would have had to come from something operating illegally or in total secrecy. Then there's the eerie timing. The WOW signal appeared in a region of space devoid of stars or known planets, but not long after, astronomers discovered that a pair of sun-like stars, almost identical in age to our own, sit nearly perfectly aligned with where the signal originated. Coincidence, or could one of those stars host a civilization advanced enough to send a targeted beacon, perhaps unaware that their message would take decades just to reach our telescopes? The deeper you dig, the more haunting the questions become. If it was aliens, why transmit just once? Was it a brief, accidental leak from a powerful communication system, like catching a snippet of a radio station as you scan the dial? Or was it deliberate, a fleeting hello from a civilization that's long since gone silent, either by choice or catastrophe? Some researchers even speculate the signal could have been a ping from an autonomous probe, left behind to monitor promising star systems for signs of intelligence. But here's the twist: the WOW signal might not need aliens to be revolutionary. Even if it turns out to be a natural phenomenon we don't yet understand, its very existence challenges our assumptions about the cosmos. It's a reminder that the universe is full of surprises, and that sometimes the most profound mysteries aren't the ones we solve, but the ones that keep us searching. For now, the WOW signal remains a cosmic Rorschach test. To some, it's proof we're not alone. To others, it's a lesson in humility, a sign that for all our technology, the universe still holds cards it hasn't shown us. But one thing's certain: until we get another signal or finally crack this one's code, that scribbled "WOW" on a decades-old printout will keep staring back at us, daring us to wonder what else might be out there, listening in the dark. In the vast emptiness of space, even the tiniest unexpected motion can rewrite the laws of physics, and that's exactly what happened with NASA's Pioneer probes. Launched in the 1970s to explore the outer solar system, these twin spacecraft performed flawlessly. Until they didn't, mission controllers noticed something bizarre. As Pioneer 10 and 11 hurtled toward the edges of our cosmic neighborhood, they began slowing down ever so slightly, as if an invisible hand were gently tugging them backward. This wasn't supposed to happen. According to Newton's laws and Einstein's relativity, their trajectories should have been predictable down to the millimeter. Yet by the time they passed Saturn's orbit, both probes were hundreds of thousands of kilometers off course, decelerating with a force 10 billion times weaker than gravity, but consistent enough to send shockwaves through the scientific community. They called it the Pioneer Anomaly. At first, engineers assumed it was just a glitch, maybe leftover fuel, leaking from the probe's thrusters or heat radiating unevenly from their nuclear power sources. But when they crunched the numbers, nothing added up. Thermal radiation could explain only a fraction of the slowdown. The rest seemed to defy explanation, as if some unseen force were at work in the depths of space. For decades, the anomaly haunted physicists, becoming one of those nagging cosmic riddles that refused to go away. Some proposed wild theories. Could it be the gravitational pull of undiscovered dark matter clumps? Or perhaps evidence of extra dimensions subtly warping space-time where the probes traveled? Then came an even stranger possibility. What if the Pioneer Anomaly was a glimpse of new physics? Not just a measurement error, but a crack in our understanding of gravity itself. Some researchers suggested modifications to Einstein's theory, introducing tiny adjustments to how gravity behaves over vast distances. Others wondered if it hinted at quantum fluctuations in the vacuum of space, where particles blink in and out of existence, exerting a minuscule but measurable drag on anything moving through them. But just as the mystery seemed poised to upend textbooks, an ordinary explanation emerged. In 2012, a team analyzing decades of telemetry data realized something everyone had overlooked. Heat from the probe's electrical systems was radiating unevenly off their antennae, creating a tiny but constant push, like a spaceship with one headlight slightly brighter than the other, nudging it off course over years. Case closed, not quite. While thermal radiation explained most of the anomaly, some physicists argue there's still an unaccounted-for residue, a whisper of something else lurking in the data. Whether it's a quirk of engineering or a signpost to deeper truths, the Pioneer Anomaly teaches us a crucial lesson about exploration. Sometimes, the universe's greatest secrets hide not in distant galaxies, but in the subtle deviations, the almost imperceptible wrinkles in reality that challenge us to look closer. And who knows, the next Pioneer might not be a spacecraft at all, but an experiment here on Earth, waiting to reveal forces we've yet to imagine. The cosmic microwave background is often called the universe's baby picture, a snapshot of its earliest light, still glowing faintly from the Big Bang. For decades, scientists have studied it like a map, expecting to find a universe that's smooth and uniform in every direction, with no preferred axis or special alignment. But when they looked closer, something unsettling emerged. The cosmos appears to have a preferred direction, dubbed that axis of evil by a skeptical physicist who joked it would destroy cosmology. This bizarre alignment in the CMB challenges one of our most fundamental assumptions, that the universe is isotropic, meaning it should look the same no matter where you're standing. Imagine spinning a globe and expecting every continent to face you equally over time, only to realize the landmasses keep drifting back toward one mysterious spot. That's essentially what the CMB reveals. Hot and cold spots in this primordial radiation aren't randomly scattered as they should be. Instead, they align along a specific axis, almost as if the universe itself has a north and south pole. Even stranger, this axis eerily lines up with the plane of our solar system, a coincidence so statistically unlikely it's like winning the lottery 100 times in a row. So what's really going on? Some theorists argue it's just a fluke, a cosmic illusion created by the way we process the data or limitations in our telescopes. Others propose more radical ideas. Could it be evidence of a pre-Big Bang structure imprinted on spacetime, like scars from a previous universe? Or does it hint that dark energy isn't uniform, but flows in currents, tugging the cosmos into alignment? The wildest possibility that we're seeing the fingerprint of something beyond our observable universe, a gravitational pull from another bubble of reality pressing against ours. The implications are staggering. If the axis of evil is real, it means the universe isn't just subtly lopsided, it might be fundamentally biased, with laws of physics that change depending on which way you look. Light could bend differently along this axis. Time might flow at altered rates. Even the expansion of space itself could vary, like a stretching rubber sheet, thicker in some places than others. Yet for all its menace, the axis of evil remains controversial. Newer satellite data has muddied the waters, with some measurements supporting the anomaly and others smoothing it away. The debate isn't just academic, it's a battle over whether we've misunderstood the cosmos on the grandest scale. Either we're seeing a statistical mirage, or the universe is quietly whispering that its deepest rules aren't what we thought. And until we know for sure, this eerie alignment will keep haunting cosmology, a silent reminder that even our best maps of reality might still be missing something monumental. The moon hangs in our sky like a silent witness to Earth's history, yet its own origins remain one of the solar system's most stubborn mysteries. Here's what makes it so baffling. The moon's composition is nearly identical to Earth's in ways that defy logic. Rocks brought back by Apollo astronauts revealed matching isotopic signatures, like geological fingerprints, suggesting the two worlds share the same cosmic DNA. But if the moon formed from a giant impact, as the dominant theory suggests, why doesn't it carry traces of the hypothetical planet-sized object thought to have collided with Earth? Picture this: 4.5 billion years ago, a Mars-sized body nicknamed Theia slams into our young planet, blasting debris into orbit that eventually coalesces into the moon. It's a clean, elegant explanation except for one glaring hole. Simulations show such a violent impact should have left the moon with a chemical makeup distinct from Earth's, blending material from both worlds. Instead, lunar samples are uncannily Earth-like, as if the moon was carved directly from our planet's mantle without any alien contamination. Some scientists argue Theia might have had an eerily similar composition to early Earth by pure chance, but the odds of that are astronomically slim. This paradox has spawned wilder theories. Could the moon be an artificial construct, placed deliberately in orbit by some advanced intelligence? While it sounds like science fiction, the idea gained traction when astronomers noted the moon's precise size and distance create perfect solar eclipses, a phenomenon with no natural explanation. Others propose the moon formed through an entirely different process, like a fission event where Earth spun so fast it flung off a chunk of itself, or even that it was captured whole from elsewhere in the solar system. But each theory crumbles under scrutiny. Capture can't explain the moon's stable, circular orbit, and fission fails to account for the angular momentum required. Then there's the mystery of the moon's missing volatiles. Compared to Earth, it's bone dry, with virtually no water or easily vaporized elements in its rocks. This suggests it endured temperatures hot enough to boil away its lighter materials consistent with a cataclysmic impact, but only if the collision was far more violent than current models allow. Some researchers now speculate there weren't one but multiple giant impacts over time, each contributing material to the moon in a chaotic construction project spanning millions of years. The deeper we dig, the stranger the puzzle becomes. Lunar seismometers left by Apollo astronauts detected mysterious moonquakes originating deep below the surface, hinting at a partially molten interior that shouldn't exist in a small, geologically dead world. Recent gravity maps reveal massive, dense structures lurking beneath its crust, likely remnants of ancient asteroid impacts, but some speculate they could be signs of artificial reinforcement. Even the moon's precise influence on Earth, stabilizing our tilt and driving tides essential for early life, feels almost too perfect to be coincidence. What if the moon isn't just a random rock, but a key player in Earth's ability to harbor life, or a relic of some ancient cosmic engineering project? Until we return with new missions to drill deeper and map its hidden structures, the moon will keep its secrets close. One thing's certain, our closest celestial neighbor isn't just a barren wasteland. It's a time capsule holding clues to Earth's violent infancy, and perhaps evidence that the solar system's history is far stranger than our textbooks dare to admit. In October 2017, astronomers spotted something streaking through our solar system that defied all expectations, a visitor from another star. Named Oumuamua, Hawaiian for scout, this mysterious object was unlike anything we'd ever seen. It wasn't just its interstellar origin that shocked scientists. It was the way it moved. First, there was its shape, long and narrow, like a cosmic cigar tumbling end over end. Most asteroids and comets are lumpy and irregular, but Oumuamua's elongated form was unprecedented. Then came the real shocker. As it raced away from the sun, it sped up as if pushed by an unseen force. Comets do this when their ices vaporize, creating visible tails, but Oumuamua left no trail. No dust, no gas, just silent, unexplained acceleration. The anomaly sparked a firestorm of debate. Could it have been a fragment of a shattered planet, ejected from another star system? Or was it something far stranger, like an artificial object? Harvard astrophysicist Avi Loeb famously suggested Oumuamua might be a light sail, a thin, reflective sheet propelled by starlight, possibly sent by an alien civilization. The idea wasn't as far-fetched as it sounded. Human projects like Breakthrough Starshot are already developing similar technology to send tiny probes to nearby stars. But not everyone was convinced. Critics argued that Oumuamua's acceleration could be explained by natural processes, like outgassing from hidden reserves of hydrogen ice, a phenomenon never before observed but theoretically possible. Others proposed it might be a cosmic dust bunny, a porous aggregate of interstellar material so light that solar radiation could nudge it without leaving a visible trace. Then there's the lingering mystery of where Oumuamua came from. Tracing its path backward suggests it drifted for millions, maybe billions, of years before reaching us. Was it a lone wanderer, or could there be countless others like it, slipping through our solar system unnoticed? Recent discoveries of similar interstellar visitors, like the comet Borisov, hint that Oumuamua might not be unique, just the first we've detected. The biggest question remains unanswered. Was Oumuamua a natural oddity or something more? The truth is, we may never know. By the time we spotted it, it was already racing out of sight, leaving behind only fleeting data and a trail of tantalizing questions. But its brief visit did one thing perfectly. It reminded us that the universe is full of surprises, and sometimes the most profound mysteries come in the smallest, fastest packages. Perhaps the most unsettling possibility isn't whether Oumuamua was artificial, but what its existence implies about the cosmos. If interstellar objects like this are common, how many might have passed by undetected? Could some even carry dormant traces of life from distant star systems, hitchhiking across the galaxy? Oumuamua's greatest legacy may be the door it opened, a door to a universe where the line between natural and artificial, between visitor and intruder, is far blurrier than we ever imagined. What if everything you remember, everything you feel, every person you've ever known wasn't real? Not in the sense of a simulation, but something even stranger, a momentary flicker of self-awareness conjured from pure chaos. This is the Boltzmann brain paradox, a thought experiment so unsettling it makes the simulation hypothesis seem almost comforting. The premise is simple yet mind-shattering. In an infinite universe governed by random quantum fluctuations, there's a non-zero chance that a fully formed, self-aware brain could spontaneously assemble out of the void, complete with fabricated memories, senses, and even an entire imaginary world. And statistically, in an eternity of time and space, these phantom minds would vastly outnumber real, biologically evolved beings like us. So here's the terrifying question: how do you know you're not one of them? The paradox gets its name from 19th century physicist Ludwig Boltzmann, who proposed that entropy, the tendency of the universe toward disorder, might not be absolute. In rare pockets, order could arise purely by chance, like a gust of wind assembling a sandcastle. Fast forward to modern cosmology, and the idea takes a surreal turn. If the universe is truly infinite and eternal, then even the most improbable events become inevitable, including the spontaneous formation of a conscious observer. A Boltzmann brain wouldn't need a body or a history. It could blink into existence for just a second, hallucinating a lifetime's worth of experiences before dissolving back into chaos, never knowing it was an accident of physics. But why does this matter? Because the paradox exposes a glaring flaw in how we think about reality. If the laws of physics allow for Boltzmann brains, then statistically, you're far more likely to be one than a product of evolution. After all, it takes far less energy for the universe to conjure a single, disembodied mind than to build an entire cosmos with galaxies, planets, and life. Some scientists argue this makes our existence evidence against an infinite, random universe, because if we were truly Boltzmann brains, we'd expect our perceptions to be fragmented and illogical, not the consistent, ordered reality we experience. Others take the paradox even further. Could consciousness itself be a fundamental property of the universe, not tied to brains at all? If random fluctuations can create self-awareness, maybe what we call reality is just one of countless ephemeral experiences bubbling up from the quantum foam. It's a radical idea, suggesting that the universe isn't just hosting conscious beings. It might be made of them in an endless dance of creation and dissolution. Yet the Boltzmann brain paradox isn't just a philosophical puzzle. It challenges the foundations of cosmology. If we accept that an infinite universe inevitably spawns these phantom minds, then every observation we make, every scientific measurement, could be the hallucination of a brain that formed 5 seconds ago. Suddenly, the entire scientific method collapses into doubt. How can we trust our understanding of the cosmos if our own consciousness might be a cosmic glitch? Here's the twist: the paradox might actually point us toward deeper truths. Some physicists propose that the very existence of stable, long-lived observers like us hints at undiscovered laws of nature, rules that prevent Boltzmann brains from dominating reality. Maybe consciousness isn't an accident, but a feature woven into the fabric of the universe. Or perhaps the paradox is a sign that infinity isn't real, that the universe is finite in ways we haven't yet grasped. Either way, the Boltzmann brain paradox does one thing brilliantly. It forces us to confront how little we truly understand about existence. Are we fleeting illusions or something more? The answer might lie not in the stars, but in the nature of consciousness itself, a mystery as vast and uncharted as the cosmos. Imagine a library where every book tells the story of a completely different universe, one where gravity is twice as strong, another where time runs backward, and yet another where life evolved from crystals instead of carbon. This isn't science fiction. It's the multiverse theory, a radical idea that our cosmos might be just one page in an infinite anthology of realities, each with its own set of physical laws. At first glance, it sounds like a wild fantasy, but some of the world's top physicists take it seriously, and for good reason. The multiverse could solve one of cosmology's biggest puzzles: why our universe seems so perfectly fine-tuned for life. Think about it like this: the constants of nature, the speed of light, the strength of gravity, the mass of an electron, are dialed to such precise values that even tiny changes would make stars, planets, and life itself impossible. It's as if someone adjusted 1,000 knobs with perfect accuracy. The odds of this happening by chance are astronomically small, unless, of course, there aren't just one universe but countless ones, each with different settings. In that case, it's no surprise we find ourselves in one where the numbers just happen to allow our existence. But here's where it gets unsettling. If every possible universe exists, then somewhere out there, there's a version of you who made every choice you didn't. A version who became a famous musician, another who never existed at all, and even one where dinosaurs evolved intelligence and built civilizations. The multiverse doesn't just suggest alternate histories, it implies that every conceivable reality, no matter how bizarre, is playing out right now in some distant corner of existence. Suddenly, our lives feel less like singular stories and more like one thread in an endless tapestry. So is the multiverse real, or just a clever way to dodge tough questions? Supporters point to cutting-edge theories like cosmic inflation, which suggests our universe ballooned from a tiny speck during the Big Bang. If inflation can happen once, why not over and over, spawning bubble universes like froth in an infinite ocean? Even quantum mechanics hints at parallel realities, with the many worlds interpretation proposing that every quantum decision spawns new branches of reality. But skeptics argue that without any way to observe these other universes, the multiverse remains untestable, more metaphysics than science, yet the implications are too profound to ignore. If the multiverse is true, it challenges our very sense of meaning. Are we special or just statistical inevitabilities? Does our universe have purpose, or is it one accidental arrangement in a sea of chaos? Some philosophers suggest the multiverse could explain why we haven't found extraterrestrial intelligence. Maybe in most universes, life never gets a foothold and we're the rare exception. Others worry it could undermine science itself, making our laws of physics mere local bylaws in a grander cosmic democracy. The multiverse blurs boundaries not just between realities, but between science and philosophy, between knowledge and imagination. It forces us to confront whether the universe is a finely tuned machine or a chaotic explosion of possibilities. And while we may never have definitive proof, the theory does one extraordinary thing. It reminds us that reality, whatever it is, might be far stranger and more wondrous than we've dared to dream. Time doesn't just move forward, it might also bend back on itself in an endless cosmic circle. This is the time loop hypothesis, a radical idea suggesting the universe doesn't have a beginning or an end, but instead cycles through infinite rebirth. Think of it like a movie reel playing over and over, with each iteration slightly different yet eerily familiar. Ancient civilizations from the Mayans to the Hindus envisioned time as a wheel, and now modern physicists are crunching the numbers to see if they might have been onto something all along. The math behind this idea hinges on the fate of the universe. If dark energy keeps accelerating expansion forever, eventually even atoms will tear apart in a lonely, frozen demise known as the Big Freeze. But some theories propose a twist, that the same force driving expansion could one day reverse, pulling everything back into a fiery crunch. Instead of vanishing into nothingness, this collapse might trigger a new Big Bang, birthing another universe with its own laws, stars, and perhaps even life. The cycle could repeat indefinitely, with each iteration leaving subtle imprints on the next, like cosmic déjà vu. What makes this more than just poetic speculation? Certain anomalies in the cosmic microwave background, the afterglow of the Big Bang, show strange, unexplained patterns. Some researchers argue these could be scars from a previous cycle, echoes of a universe that existed before ours. Even the distribution of galaxies on the largest scales hints at a universe that's not entirely random, as if it's carrying faint memories of an earlier incarnation. But here's where it gets truly mind-bending. If time is cyclical, does that mean every event, every choice, every life repeats exactly as before? Or does each cycle introduce tiny variations, like a cosmic game of telephone where the story shifts slightly with each retelling? Some interpretations suggest free will could still exist within the loop, with infinite versions of history playing out across successive universes. Others propose a darker twist, that every moment from the birth of stars to the rise of civilizations is predetermined, locked into an unbreakable sequence. The implications ripple far beyond physics. If the universe is caught in an eternal return, then every tragedy and triumph, every act of love or cruelty, has already happened countless times before and will happen again. It's a thought that can either fill you with despair or a strange kind of comfort, knowing that even if our universe meets its end, another will rise from its ashes. The time loop hypothesis doesn't just challenge our understanding of reality. It forces us to confront what it means to exist in a cosmos where beginnings and endings might just be illusions. At the heart of quantum mechanics lies one of the most unsettling truths about reality. Particles don't behave like tiny billiard balls bouncing predictably through space. Instead, they exist in a haze of possibilities, only settling into definite states when someone or something pays attention. This is the quantum observer effect, a phenomenon so counterintuitive it makes even seasoned physicists pause. Picture an electron whizzing around an atom. Before measurement, it's not in one location but smeared across a cloud of probabilities. The instant you try to pin it down, the cloud collapses and the electron chooses a position. It's as if reality itself hesitates until we look, then snaps into focus like a shy actor stepping into the spotlight. The implications are staggering. If particles truly change their behavior based on observation, does that mean consciousness plays an active role in shaping the universe? Some interpretations of quantum mechanics suggest exactly that the very act of measurement doesn't just reveal reality but creates it. In this view, the world isn't a static stage waiting to be discovered. It's a fluid, participatory dance where mind and matter intertwine. The most famous demonstration of this is the double-slit experiment, where particles like electrons or photons behave as waves when unobserved, creating interference patterns, but switch to particle-like behavior the moment a detector is turned on. It's as if the particles know they're being watched, adjusting their performance accordingly. But here's the catch: the observer effect doesn't require human consciousness. A machine recording data can trigger the same collapse. This has led to fierce debates. Is it awareness that matters, or just any interaction with the environment? Some theorists argue that consciousness is fundamental, that the universe only becomes concrete when perceived by a mind, whether human, alien, or artificial. Others dismiss this as mysticism, insisting the observer effect is purely about physical interactions, not sentience. The truth might lie somewhere in between. Consider the possibility that reality exists in layers. At the quantum level, it's a shimmering fog of potentialities. As we scale up to everyday objects, these probabilities solidify into the stable world we recognize, not because consciousness magically conjures it, but because trillions of quantum interactions average out into predictability. Yet even this explanation feels incomplete. Why should observation have any effect at all? Why doesn't the universe just chug along independently, indifferent to whether we're watching? The quantum observer effect blurs the line between science and philosophy, forcing us to confront questions that once belonged to metaphysics. Are we passive witnesses to an external world, or active participants in its creation? Does the universe need us to exist, or are we just fleeting patterns in a vast, indifferent cosmos? One thing's certain: the deeper we probe the quantum realm, the more it challenges our most basic assumptions about what's real, and whether reality is even the right word for the strange, shimmering spectacle we call existence. The Big Bang should have been the ultimate cosmic balancing act, creating matter and antimatter in perfectly equal amounts. These twin counterparts are nearly identical, except for one crucial difference: their charges are opposite. When they meet, they annihilate each other in a flash of pure energy, leaving nothing behind. According to all known physics, the early universe should have produced both in equal measure, meaning everything should have cancelled out instantly, leaving behind a lifeless void of radiation. And yet, here we are. Stars, planets, and life itself exist because somehow, against all odds, matter won out. For every billion particles of antimatter born in the Big Bang, there were 1,000,001 particles of matter. That tiny, inexplicable excess is the only reason anything exists at all. This cosmic accounting error is one of physics' greatest unsolved mysteries. Where did all the antimatter go, and why was the universe left with even a shred of matter to build galaxies and people? The problem is so perplexing that Nobel laureate Richard Feynman once called it the most striking phenomenon in all of physics. If we could rewind time and watch the first moments after the Big Bang, we'd see a seething, symmetric soup of particles and antiparticles, constantly colliding and annihilating. Yet by the time the universe was just a second old, almost all the antimatter had vanished, leaving behind a faint residue of matter, just enough to eventually form everything we see today. Scientists call this imbalance Baryon asymmetry, and it's a clue that something fundamental is missing from our understanding of the cosmos. The standard model of particle physics, which has brilliantly explained so much, falls utterly short here. It predicts a universe that should have annihilated itself into nothingness. Clearly, nature has a trick up its sleeve, one we haven't discovered yet. Some theories suggest undiscovered particles interacted differently with matter and antimatter, tipping the scales ever so slightly. Others propose that antimatter might have hidden properties causing it to behave in ways we can't yet detect, like decaying faster or even being repelled by gravity. Then there's the wilder possibility: what if entire regions of the universe are made of antimatter, lurking just beyond our observational reach? Imagine distant antimatter galaxies, antimatter stars, even antimatter life, all invisible to us because the space between us and them is filled with normal matter, creating an impenetrable annihilation barrier. It's a tantalizing idea, but so far, telescopes have found no evidence of these hypothetical anti-worlds. Even cosmic rays, which occasionally bring particles from deep space, show no signs of antimatter arriving from distant corners of the cosmos. The search for answers isn't just academic. If we can uncover why matter dominates, we might crack open entirely new chapters in physics, perhaps revealing particles or forces beyond the standard model. Experiments like the Large Hadron Collider are smashing particles together at unimaginable energies, hoping to catch a glimpse of the subtle differences between matter and antimatter that could explain the imbalance. Meanwhile, astronomers scan the heavens for any trace of primordial antimatter, and labs like CERN Alpha experiment meticulously study antimatter atoms, measuring their properties with breathtaking precision to spot even the tiniest deviation from their matter counterparts. But here's the profound twist. This isn't just a puzzle about the past. The fate of the universe hinges on it. If matter and antimatter were perfectly symmetric, reality as we know it wouldn't exist. The fact that we're here at all means the cosmos played favorites, and that bias, whatever its cause, is woven into the fabric of everything. Solving the antimatter mystery wouldn't just rewrite physics textbooks. It would tell us why the universe allowed itself to exist, and whether, in some other reality, the antimatter won. What if the three-dimensional world we perceive, the depth of space, the solidity of matter, even the passage of time, is nothing more than an elaborate illusion? This isn't the plot of a sci-fi movie. It's the holographic principle, one of the most radical ideas in modern physics, suggesting that our universe might be a two-dimensional projection, like a cosmic hologram encoded on the edge of reality. Think of it like a credit card hologram. Tilt it, and a flat surface suddenly appears three-dimensional. Now imagine that same trick applied to the entire cosmos, with every star, planet, and person just a shimmering mirage emerging from information etched onto some distant, unseen boundary. The roots of this theory trace back to an unexpected place: black holes. In the 1970s, physicist Jacob Bekenstein discovered that the amount of information a black hole can contain isn't proportional to its volume, as you'd expect, but to its surface area, specifically the area of its event horizon. It was as if the black hole's interior was somehow being described by its two-dimensional boundary. Decades later, string theorists like Leonard Susskind and Gerard T. Hooft took this idea further, proposing that the entire universe might operate the same way. In their vision, the three-dimensional space we inhabit could be a kind of projection, with all the information needed to construct reality. Every particle, every force, even your thoughts, stored on a vast, flat surface at the edge of the cosmos. But how could this possibly work? Imagine watching a movie on a screen. The images appear to have depth, movement, and life, but in reality, they're just patterns of light emerging from pixels on a flat surface. The holographic principle suggests our universe might be like that movie, with the screen being something called the cosmological horizon, the farthest point light could have traveled since the Big Bang. Every event, every object in our 3D world would correspond to tiny, intricate fluctuations on this distant surface, like ripples in a cosmic pond encoding the illusion of depth. The implications are staggering. If the holographic principle is true, it would mean that space itself isn't fundamental but emergent, a kind of collective hallucination woven from quantum information. Time, gravity, even causality might just be side effects of this deeper, two-dimensional reality. It's a concept that turns our intuition inside out, suggesting that the solidity of the world around us is as fragile as a shadow cast by firelight. Yet for all its strangeness, the holographic principle isn't just philosophical speculation. It's a mathematically rigorous framework that could solve some of physics' biggest headaches, like unifying quantum mechanics with general relativity. In a holographic universe, the fuzzy, probabilistic rules of the quantum world and the smooth geometry of spacetime wouldn't be in conflict. They'd just be different perspectives of the same underlying code. Some researchers even suggest that the principle might explain dark energy, with the accelerating expansion of the universe being a glitch in the cosmic projection, like a video buffering at the edges. But how could we ever test such an outlandish idea? Surprisingly, there are ways. Physicists are hunting for evidence in the cosmic microwave background, the afterglow of the Big Bang, looking for patterns that might reveal a pixelated structure to spacetime. Others are studying quantum entanglement, where particles remain mysteriously connected across vast distances as a possible signature of hidden, lower-dimensional links. Even the Event Horizon Telescope, which captured the first image of a black hole's shadow, could provide clues by checking whether black holes behave as if their information is stored on their surfaces. The holographic principle doesn't just challenge our understanding of space, it redefines what reality might be. Are we living in a simulation? Not exactly. It's more profound than that. We could be shadows cast by something far simpler, yet unimaginably complex. A universe where the truest version of everything exists not in the world we see, but on a distant, flat frontier we'll never touch. If that's the case, then the greatest magic trick of all isn't pulling a rabbit from a hat, it's convincing us that the hat, the rabbit, and even the magician were ever three-dimensional to begin with. From dark matter's ghostly presence to the holographic universe's dizzying illusions, these 18 cosmic mysteries don't just push the boundaries of science, they shatter them completely. What's truly humbling isn't just how much we don't know, but how many of our most basic assumptions about reality might be utterly wrong. The universe isn't merely hiding secrets, it's whispering in riddles, teasing us with paradoxes that defy logic and stretch imagination to its limits. Every discovery peels back another layer, revealing not answers but deeper, more tantalizing questions. Consider this: each of these clues, whether it's quantum entanglement's spooky connections or the Great Attractor's invisible pull, is like a single thread in a tapestry we can't yet see. Pull one and the whole picture shifts. Maybe dark matter isn't a particle at all, but a shadow cast by another dimension. Maybe the Big Bang wasn't a beginning, but a rebound from some earlier cosmic cycle. The beauty of these mysteries isn't just in their strangeness, but in how they force us to rethink everything we thought was settled. Science isn't a static set of facts, it's a living, breathing conversation with the unknown. And here's the most thrilling part: we're just getting started. New telescopes peer deeper into space, particle colliders probe finer details of matter, and simulations recreate conditions a fraction of a second after the Big Bang. With every tool we build, the cosmos tosses us another curveball, another "wait, that shouldn't happen." That's the joy of it. The universe isn't a puzzle to be solved, but an endless frontier to explore, one where the rules might change when we least expect it. So what do you think? Are we on the verge of breakthroughs that'll rewrite the textbooks, or are these mysteries destined to outsmart us forever? Drop your wildest theories in the comments. Maybe one of them will be the next big revelation. And if you're craving more journeys to the edges of understanding, hit subscribe and ring the bell, because out there, in the vast dark between the stars, the next great cosmic surprise is waiting, ready to blow our minds all over again.